or mud, is one of our planet's most versatile materials. Receptive and plastic, earth has been used in building for thousands of years. These buildings from the Middle East and North Africa show what can be done using only sun-dried mud. They are beautiful and economical, but wind and rain will erode them. They are not durable. The ancient art of pottery gives durability to earth by firing it at high temperatures. Heat transforms clay into a hard, waterproof substance. In 1975, the Iranian architect Nader Khalili boldly brought together the techniques of mud architecture and pottery by building a 10-room school and then firing it as a whole. Khalili's experiments were closely followed by Ray Meeker, an American settled in South India.
I won't say I studied architecture. I'll say I attended architecture school in the university at one point in my checkered career. And at the same time, I was studying ceramics. Now, I've been in Pondicherry for 17 years, running a pottery. And a few years ago, I was attracted by the idea. Actually, I heard of Nader Khalili, so I looked him up, and we spent a little bit of time together.
Ray saw the potential in Khalili's technique for meeting India's staggering demand for durable, low-cost housing. But the problem of fuel consumption had to be overcome. So Ray decided to treat the mud structure as a kiln, fill it with raw bricks that would get fired along with the structure, and then sell the bricks to offset the fuel costs. Ray made several small-scale experiments. They worked. Then, in 1987, Ray would get a chance to test his method on a large scale when two friends of his decided to build a home in Auroville near Pondicherry. They asked Ray to design and build for them a fired house, which they christened Agni Jata, a Sanskrit name meaning fire-born. The earth at the building site will largely determine the cost of a fired house. It should be good enough for making fired bricks. This is a difficult criterion to meet. Most earth is unsuitable for fired bricks, and the earth on this site, a sandy lateritic clay, is no exception. Brick clay, trucked in from 15 kilometers away, had to be mixed with the on-site clay. Many bricks were discarded before an adequate mixture was found. Agni Jata will consist of a central domed room of 5 meters diameter and 4 vaults, making 80 square meters of living space. The foundation is made of fired brick in lime mortar with a damp-proof course in cement mortar. The whole structure is set about 75 centimeters below grade for 2 reasons. One, aesthetic, to achieve high interior spaces as unobtrusively as possible, and the other, structural, to allow the earth itself to act as the primary buttressing material.
This is not strictly a mud-only building. We use a composite wall of a fired brick and a mud brick. We do that because in our climate we have a very severe monsoon season. It's not a long season, but it does rain heavily. And I know we cannot fire through the wall to really create a water-resistant exterior. So we use a composite brick wall, we use a fired brick on the outside, and we use a mud brick on the inside.
So far, this is easy work for the local masons, who are used to building with mud brick and mud mortar. Now the vaults begin. This frame describes a catenary curve and is used to lay 4 arches. The frame is raised and leveled by a bolt at each of the four corners. Raising the frame will allow for its removal when the arch is completed. Mud arches and vaults without centering of any kind is an absolutely new technique for the local masons, and it's not easy for them. The traditional vault of the Middle East or Egypt begins by leaning the first brick against a supporting wall, or against an arch in this case. The second course of brick is pitched at a slightly greater angle, the third course at an even greater angle, and so on, until the desired angle is reached, about 75 degrees. This is a 2-meter high vault with a 3-meter span, so it will take about 10 courses of brick to reach the correct angle. The vault is then continued at that angle to its full length. Vault, no mortar should be used between bricks in the same course. On the exterior, where the parabolic curve makes gaps between bricks inevitable, bits of dry brick are tightly packed in the open joints. On the interior of the vault, the bricks touch one another. Mud mortar can shrink as much as 35% while drying. So if mortar is placed between bricks, this shrinkage will cause distortion of the curve. In a structure that will eventually be fired, this could cause cracking or even total failure of the vault. At this stage, the masons are still untrained in Nubian vault building, and they are slow. After another week's practice, they were laying a respectable 1.5 linear meters a day. The arch frame now makes a good guide to help the masons maintain the catenary curve of the vault. The dome grows simultaneously with the vaults. A dome is not difficult to build. It will take its shape from a trammel 2.5 meters long. The trammel is fixed on a post at the center of what will become the hemisphere. The trammel rotates full circle in the horizontal plane and through 180 degrees in the vertical plane, so it automatically locates any point on the interior of the dome and gives the inclination of each course of brick. This mason had never built a dome and was the least skilled of the 3 masons working on the house. With disbelief, which increased directly with the height of the dome, he slowly and at times reluctantly worked his way to the central skylight. As the dome progresses towards the top, the bricks are pitched to one side, slightly out of the radial line. This allows each brick to hang both on the ring below it and on the previously laid brick. Rain could be disastrous for the house in its raw state, so a lot of time and labor goes into covering and uncovering the structure every day. This is supposed to be the dry season, but why take chances? Once the dome and vaults are finished, a number of details remain. A row of holes on either side of each vault will be the exit flues for the water smoking period during the first 2 days of firing. The walls are temporarily buttressed with earth to counteract horizontal expansion of the house during firing.
In a conventional building technique, we would now be ready to begin the finishing work. We would plaster, put in the windows and what have you. Here we have an intermediate stage, which is, it's important and there's a great deal of potential in it, but it's not without problems. We have to fire this house, and we cannot really fire it empty. Probably the fuel cost alone, firing it empty, would come to building the same structure in fired brick and lime mortar. For the last 4 months here at the pottery workshop in Pondicherry, while the construction of this building has been going on, we've been making products to fill the building, fill the house for the firing. We're trying to develop a small-scale industry for making fired clay building products, so that when you fire this structure, that you have products that will go into either other buildings or into the same building when it's finished. For instance, the floor tiles of this building will all be fired in the building.
For each product has its own preparation method. This liquid clay, sieved and dried, is meant for the extrusion process. Pipes, hollow building blocks, and many other shapes can be made in this simple, inexpensive extruder. Here, slabs of rolled clay are used in the press molding technique.
You have to have look at it. Move the side first and then the side.
The result is a toilet pan.
By far the most significant part of this product load will be table molded bricks. It's for two reasons. The main one is because it's the only thing we can really make rapidly enough to fill this structure. But very important also is the fact that we use a great deal of fuel to fire this house, and bricks take a correspondingly large amount of fuel. 60,000 to 80,000 bricks will go into this structure, and it will require a comparable amount of fuel to fire those bricks.
Because the clay at the house site is unsuitable for making high-quality bricks, the cost of this experiment is very much increased. Clay used in these bricks was first transported from the brick fields to the pottery workshop. The bricks are now being taken to the house site. The transportation cost of 150 cartloads of bricks and tiles is not insignificant.
Just check the front line to see that it's going straight across.
Yeah, that's what I'm doing. That's why I'm bending
Okay. The stacking of this structure took nearly 4 weeks to complete. That seems a bit absurd, but in fact, it's the stacking itself which really determines the way the heat will move and how well and evenly fired the building and the product will be. So I'm really stacking this structure and making decisions practically each time I put down a brick as to how open or closed the stacking should be at that particular point, which means I put myself in the rather unenviable position of having to stack nearly all 60,000 of these bricks myself. This is a mixture of 2 parts rice husk, 1 part cow dung, and 1 part of clay. It's used as an insulation It's placed over the vaults and dome in a layer 10 centimeters thick. In the early stages of the firing, it acts solely as an insulation, and towards the end of the firing, because it's composed of organic material, it burns. Thereby, we get heat from the inside, from the firing of the interior, but we also get a combusting layer over the vaults and domes. So actually, the vault and dome is really fired from two sides.
The biggest challenge to fired building technology is the efficient use of fuel. Firing Agni Jata meant stocking 40 tons of casuarina pine and 3,000 bundles of pine branches. Casuarina wood is the most efficient and inexpensive fuel available here. Casuarina is grown extensively in South India as a fuel crop, and the villager, who is meant to be the beneficiary of this fired house technique, understands planting, tending, and harvesting the trees. The pine branches now make an additional protection for the house against the threat of rain. And rain it did. One night, 7 centimeters fell in an unseasonal cloudburst.
Still here?
Yeah, still here. In fact, I think we realized really that it is an experiment when the first rain came. And then we were in our bed, and then at that time we really felt that the experience could finish in a catastrophe.
I think it's okay.
It's okay?
I mean, I don't think there's anything to do about it. Just we clean out this mud,
Okay.
make a better trench,
Yeah.
and whatever is done, it will dry. I don't think it's too serious.
Okay.
Thanks to the careful protection, the minimal rain damage was easy to patch up. Then the whole house gets a thin coat of mud mortar, the last step before the firing begins. The firing begins in the vault fireboxes. The first stage, which takes about 2 days, is called the water smoking period. During this period, the water, as much as 10 tons of it, is evaporated from the vaults and walls, and then from the bricks and tiles stacked inside. The steam escapes through the smoke holes in the top. When the water smoking is finished, these vents are closed and the stoking is accelerated. The heat now travels through the vaults and into the dome, pulled by the dome vents and downdraft chimney. After the vaults reach maximum temperature, stoking starts in the dome.
A dome, for instance, is a standard kill shape, and a vault also is a standard kill shape. But to combine the two and to combine 4 vaults around the one dome, there is no model for that in firing technology. It's not going to be a particularly efficient kiln. We're now halfway through the third day of this firing operation. It's taken about nearly 60 hours to get the draft moving. Three of the chambers have been working pretty well, but this particular chamber, we've been having a very difficult time getting air sufficiently deep into the chamber in order to combust the fuel. I don't know, occasionally you'll see the flame burning back here, the smoke comes here. That means we've got pressure back. We're back burning the fuel. That means, in fact, not air, but really carbon monoxide is coming through the rest of the building and pushing the flame really out, not allowing the chimney to draw the flame in at this point. We have 5 thermocouples connected to these pyrometers, one for each vault and one for the dome. And we take hourly readings at this point, and then when the firing becomes a little more rapid, we take half-hourly readings simply to keep a record and to understand how we're moving, at what rate we're gaining temperature. This is the large vault, and we've brought this vault up to around 350 or 360 degrees centigrade. And we're beginning the full fire on this side now, mainly for my own peace of mind. I want to see if we can start moving this thing. And that means we're taking what we call melar here. It's actually the tops of the casuarina pine. They just lop off the tops and they put them into these bundles. And it makes a very convenient way to put in quite a bit of fuel in one stoke. We can shove it quite deeply into the firebox. This is the morning of the 4th day. The temperature's rising, but the heat distribution is still pretty uneven. So I think after we get up another 100 degrees, we're at about 600 now. We'll have to start trying to figure out how to even out the temperature. That probably means that I won't sleep again tonight, as I didn't last night. I hadn't expected the dome to become so hot so early, but we have so much preheated combustion air coming in to the dome from the vaults that it burns the wood very, very efficiently. And we've made a very rapid temperature increase. We're 980 degrees now in the dome. We've just had a door collapse between the big vault and the dome on this side. One of the doors, which is stacked filled with bricks as a bag wall, has just fallen. So it's obviously time to stop. It's obviously too hot in there now to continue stoking. So we're finished at about 980 degrees centigrade.
Every opening is tightly sealed for a slow cooling down. After 3 days of cooling, the house is opened. 3 more days, and results can be seen at last. These 60,000 fired bricks will be sold to another construction site and will pay for the cost of the firing.
Anytime you fire a structure of this size, you're bound to have hot and cold spots, which we certainly have. But for the most part, Agni Jata has been very well fired. It's water resistant. It will not dissolve in a rain, but it is not waterproof. Now we're pounding lime for the exterior plaster. As an experiment, Agni Jata was invaluable. It demonstrated that you could really stabilize a large mud structure by fire, and it pointed out very clearly that we need to work on cutting down the fuel consumption. Right now we've started a small test village house in a village near Pondicherry, which should really tell us if there's the potential for making this a low-cost process.